Okay, so back to unit 4B, I believe, and these really only apply to covalence. Remember, because in our ionic bonds, the electrons aren't shared, they're transferred. And VSEPR stands for valence shell electron pair repulsion. So we're talking about how the electrons, those negative electrons, how they repulse each other. All right, so we don't have to remember all of them. There's actually many, many more than these four that we have listed here. But you do need to remember, of course, that electrons are negatively charged and that they pairs well repel each other. Sort of gets us our name, valence shell electron pair repulsion. Whoops. And the molecule shapes are determined by the number of shared and unshared pairs and how they're organized. So we can look at a couple examples. For example, linear. Linear should make sense. It's going to be something like here's one molecule, one atom, and here's our middle atom, and here's the third. So this could be like CO2. Very linear. CO2, carbon dioxide is linear. Very balanced. Those two O's are exactly repelling the same amount, so it doesn't bend. In terms of bent, we could talk about, let's go with SO2. Sounds very similar, right? SO2, CO2, but in this case, there is a little bit different geometry going on, and the S actually ends up with this unshared pair up here. And, oops, O. There. And the way it bends, it tends to bend because this unshared pair pushes it apart. And so you would see something like that. Water was another example of a good bend. Very good bend. Okay, so if you go and you look at the internet or extra pages, you're going to see that there's tetrahedral, triagonal, pyramidal. There's other bents with two unshared electron pairs. There's triagonal, bipyramidal, seesaw, T-shaped, linear, all sorts of other different ones. But we're pretty much sticking with these very few. So tetrahedral, a good example of tetrahedral would be CH4. And this one's sort of the camera on the tripod. All right, where we have C, H, 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 H. And they're all trying to get pretty far away from each other. If you look online too, you'll see that there's a fairly fixed relationship with those different angles. But CH4, typically you've got 5 atoms involved. 1, 2, 3, 4, 5. Typically in here you've got 3 atoms involved. You've got 3 atoms involved. How about the triagonal pyramidal? It's sort of like this tetrahedral, but instead of an atom up here at the top, we've got, that's where our unshared pair is. And so like NH3, ammonia, is a triagonal pyramidal. So that instead of being occupied by an atom, we have this unshared pair. So this is only going to have 4 electrons, or excuse me, 4 atoms involved in it. So quick rule of thumb with the ones we have to worry about: 3, 3, 4, and 5. The next section is all from 4C, and it's all that percent composition. And sometimes you guys are going to need more space than this. I will probably try to write it both on this page, and I have some blank pages floating around underneath my stack that I can use if I run out of space. Please make sure that as you're doing your work, you're writing big enough that you can keep track of and neat enough that you can follow. So if we look at this bottom of the page, phosphoric acid, H3PO4. So phosphoric acid is used in detergents, fertilizers, toothpaste, and flavoring in carbonated beverages. Calculate the percent composition by mass to 2 decimal places of the three.
Good afternoon. Kirk Bain to the front office, please. Kirk Bain to the front office for a visitor. Thank you.
Oops, sorry. All right. So 1, 2, 3. So hydrogen, phosphorus, and let's just write them. Hydrogen, phosphorus, and oxygen. So first thing we need to do is we need to write down, there's 3 hydrogens, and they're all 1 gram per mole. Okay, phosphor, there's only 1 phosphorus in each, so 1 phosphorus, and you need a periodic table. So if you grab your periodic table, phosphorus is 31 grams per mole. And lastly, there are 4 oxygens. Sorry about the way I'm stretching this out. Hydrogen, phosphorus, oxygen. 4 oxygens, and they are each 16 grams per mole. It is okay if you want to give a few more decimal places. They did say 2 decimal places, so you could give me 15.99 if you want to. So if we're going to do this, now we have to add that up. There are 3 times 1 hydrogen, so that's 3, plus 31 phosphoruses. Let's just go ahead and put our pluses in here. Okay, so 31. So now we have an additional 4 oxygens. So the total mass of this is 98 grams per mole. All right. So out of that 98, we said 3 was hydrogen. So hydrogen, 3 out of 98, and let's make it a percent. So 3 divided by 98 gives me 3 point, what they say, 2 decimal places, 3.1%. Phosphorus, 31 out of 98. 31 divided by 98 times 100 gives me 31.6%. And lastly, our O, which is 64 out of 98. And you guys should be able to tell me what this should equal, because if we've got to add to 100 and we've already accounted for some, let's just check. 64 divided by 98 times 100 gives me 65.3. And if I add up 65.3 plus 31.6 plus 3.1, oops, I get 100%. So this would be the percent composition. So if I ask you what's the percent of this molecule that is oxygen, you can say, well, this phosphoric acid is 64 out of 98, or 65% oxygen. Okay, so this is another one that tripped you guys up all the time. Percent composition of water in aluminum oxide hexahydrate. So let's write aluminum. And aluminum is always a +3. We can just scribble that in real lightly, +3. Oxygen, oxygen's always a -2. So we're going to cross those. Al2O3. Hexa is 6 hydrate. So if I'm looking at this and adding it up, I'm going to look and find out aluminum. Aluminum is 27. There's 2 of them. Plus, there's 3. Oxygen is 16. Plus, let's put a big parentheses. There's 6 of these. So 2 hydrogens, 2 times 1, plus 1 oxygen, 16. This is all my water. So if I do 2 times 27 plus 3 times 16, I get 102, plus I have 6 waters, and water is 2 plus 16, that's 18, times 6. I get 108. is water. So if you add these together, that's 210. Let's close that off. 210 grams per mole. And you guys can look at it. This is 102, that's aluminum oxide, and 108, that's the hexahydrate. So this is, you could almost say it's 50%, right? Almost 50-50. But if we want to get the actual number, this is our hydrate, 108 divided by 210 times 100. It is 51.4% water. Aluminum oxide hexahydrate is 51.4% water. Please go through, do some practice. You can pick any molecule you want to and do it for practice and determine the percent composition.